What is the meaning of this?
Pushcar is in the name, and I think it has.
Oh, no way. You're not
Yeah.
the one understanding.
You're trying to tell a Jason joke right now, and
This was not Jason.
It was a Jason joke.
No.
Yeah, a Jason joke.
Really?
Yeah, this Jason's crazy.
What's up?
Oh god.
That's amazing, guys.
Let's move on to stuff.
We've been started.
Okay. This is paper 11, mechanical behavior and solid solution strengthening model for FCC single crystalline and polycrystalline high-entropy alloys. I feel like we've gone over HEAs, but high-entropy alloys contain 5 or more principal elements that are in equal or near equal atomic percentage with FCC, BCC, or HCP structure. Single-phase HEAs form stable solid solutions without precipitates. So this allows us to look at the strengthening mechanism. The issue described in this paper is that due to the severe lattice distortion from atomic differences, intrinsic lattice resistance or dislocation glides specifically, this affects the solid solution strengthening that plays an important role in yield strength. So there on the right, I have yield strength pinpointed, which is like the point of no return, pretty much, for materials. Which is obviously, like, we all know, a very common mechanical property in materials. They mentioned these other, like, all these different models, but the specific one that they mentioned or, like, incorporated in their research is this work by, or a model by the Yi group, or some Yi group, that proposed a geometric model for intrinsic residual strain in HEAs that accounts for atomic size, atomic fraction, packing density, yada yada. They use the COCR, FEM, and NI, which is, I think, listed in another paper as I'll give it a name. I don't remember now. I probably should have looked it up, but that's not irrelevant. But it's like, I don't know, class of, some guy like found this class of materials and he named it after himself. So they look at the mechanical behavior, specifically critical shear stress, or CRSS, which is the stress resulting from mechanical or thermal force applied in shear, and it's critical when it's higher than the threshold for dislocation. So just basically like the amount of shear stress it takes. And then they create a solid solution strengthening model for estimating intrinsic yield strength using residual lattice strain that they develop, or that they find, and the CRSS that they calculate. And then down there is like an example of dislocation glide, or like dislocations. And you can have it happen by plane, but I think here they're doing it by like individual lattice. I don't know. That's technically a GIF or a video that I just took a screenshot of. But if you look up dislocation glide, like there's good visuals for it. But yeah. So their experimental procedure, they use the Bridgman growth method, which actually is how a lot of ferroelectric and piezoelectric perovskites are made, which is interesting. It's just like it reliably produces single crystals, specifically being ingots, and you can see that they clearly are making like these like rods. And they grow from melt, so it's just like high temperatures, good purity. They made 5mm diameter rods in 100 and 110 growth directions. They used XRD and EBSD for crystal orientation, SCM for chemical composition, and then a UTM, which is like a mechanical testing apparatus for compression testing. And they conducted at a constant strain and at constant temperature, at room temperature. And the rods that they did for the UTM were 2mm and 4mm in diameter. Or no, 2mm in diameter, 4mm long. And then they used DIC to identify slip planes. So those are like their tools for characterization. So then they went into some theoretical modeling. Yield strength being the intrinsic lattice friction stress, delta F, or sigma FR, the solute, the like structure of solute atoms, and then they go into like initial dislocation density, precipitates, and grain boundaries. But then they mentioned that initial dislocation density is low and there are no grain boundaries, and also the single phase of this class of alloys has no precipitates in its initial microstructure, so the last three terms can be crossed out, so you're left with the intrinsic lattice friction stress and the structure of the solute atoms, which they kind of like combine together. Yeah, into this this new equation, which they're including, or they're like being able to get the strengthening effect due to lattice distortion. So that's what they call this, like sigma y or sigma 0, which is the lattice friction stress, which is what they kind of like refer to this for the rest of the paper. They say that this intrinsic yield strength is attributed to atomic size and modulus shift, but here they're only looking at atomic size. So I guess something to consider in the future is that there are other factors that account for this, but they're only looking at one.
Isn't the lattice friction stress just how things move when things are strained along the lattice?
Mm-hmm. Yeah, which is why then they are looking at dislocation glides, because if they look at the glide planes, or the planes where glide is happening, they're able to account for this friction stress because it's happening at those locations. And this is normalized by dividing by elastic modulus. I don't know why, but or maybe they mentioned it. So. For alloys with no elastic modulus, they use this equation. Really relevant. So since HEAs have various principal elements, there's a lot of lattice distortion, which hinders the movement of dislocations, which yields to an increase in yield strength. And then they're using the Yi model to quantify this like geometric association. Then they do root mean square, residual strain was calculated, and they're analyzing the relationship between residual strain and intrinsic yield strength, which I think is like some of the charts or stuff that they did. Then they go into lattice friction that they characterize theoretically and experimentally. Experimentally, they did this through the CRSS calculation, and theoretically, they found that this lattice friction stress expresses a function of residual strain using the Yi model again. So they do all this, and then they get their equation, their like solid strengthening equation or model for these HEAs. And they mention like this sites radius. Basically, these are the atomic radii they use. So now results and discussion. So this is them basically like using XRD and EBS to like prove they grew single crystals, no precipitates, and high quality single crystals of this like alloy, this like alloy class. They did it, yay. Okay, now we're going into mechanical properties. They do this by true strain as a function of, or work hardening rate, and true strain, work hardening rate is the increase of stress necessary to continue plastic deformation. I don't know why they use work hardening rate specifically. I thought there was like a kind of niche rate to use, but whatever. They show these trends, stage 1, stage 2, stage 3, which is typical of FCC crystals, of single crystals. And this stage 1, 2, and 3 is easy glide, linear hardening, and parabolic hardening, which is just like a known characteristic of FCC single crystals. And then the image there down on the right at 0, which is like correlates with the graphs, at 0.1 true strain, there's a single slip line, which is like the red dots. It's, I don't know, kind of hard to see here, but you can see it in the paper. Versus in the single crystals, okay, so single crystal 1, 0, 0, and then 1, 1, 0, they revealed only one slip line, versus 2 slip lines. And then they found a secondary slip line, which is the yellow dotted line at 0.3 true strain. So clearly, like, there's 2 different process or 2 different steps happening, which means that this slip is occurring at another slip system at the second stage of the work hardening. So they're trying to show that, like, these different stages and these different like easy glide, linear hardening, parabolic hardening. Different slips are happening in different slip systems, and they're happening at different times. And then they found that the yield strength is 117 megapascal for both 100 and 110 single crystals. Then they go further into mechanical properties. They found the yield strength for the polycrystalline alloy was 326. They use Schmidt law to calculate CRSS. And then I have included here some stuff about it, which is basically like the shear force along the slip direction divided by the area of the slip plane. Yeah, it might be good to like review some of that stuff. It has a lot of, I don't know, I feel like it's stuff that we didn't do in crystals that he probably should have done in crystals, but didn't have the time
I
to.
feel like I saw that in my intro in my C class, but like, no.
Yeah.
Yeah. I think it's more applicable with like metals. or
Yeah,
stones.
yeah, yeah.
Okay.
There's a quarter of crystals that's gone missing since like 2 years ago.
Yeah.
Dislocation.
Pretty
Instead of
much. So I heard that people said that they, in the past, have been asked questions in quals based on this kind of stuff, but that was because they actually did it in class.
I've seen
they
some
were
of the
smart.
past questions that like there's even kind of calculations on this.
Yeah, which the tough part is like we don't, since we didn't go over it, like I don't know.
We don't have the background.
Yeah, if they were smart, like they obviously wouldn't ask us questions. Not necessarily like.
They were aware what was in the class.
Right. So that's the thing is like I don't know. I don't know if they're like if they came together they were like, hey, the students this year like didn't really learn this stuff, like maybe let's ask them, not ask them to like do any calculations, but I think like theoretical stuff is good. Like even just like knowing what the Schmidt law is, or at least like this equation like tau RSS over FS and A1, like at least knowing like what like how it correlates to the like diagram and like the slip and everything. Then they do a Hall Petch plot, which is the grain size dependence of yield strength. This was mentioned in what am I thinking of? Oh, scattering class, where it's like yield strength and like lattice spacing. And I think in one of the other channels I uploaded like the class notes from that class again. I mean you can look it up online too, but yeah, so yield strength of the polycrystalline material was plotted as a product of the tau CRSS, like the Schmidt law or CRSS as they're like referring to it. Using this equation, they multiplied this like tau by m, which is a Taylor factor, which just describes the total amount of slip activity, and it's like a set constant. So it's 3.06 for FCC polycrystals. So that's what they're using. And then it's fitted with experimental parameters that they mentioned here. And then sigma naught, which was this original, where is it? Here, the sigma naught is like lattice friction stress, which is kind of what they're trying to figure out, or like characterize. Corresponds to infinite grain size and is the solid solution strengthening effect in HEA considered. So this is like this like sigma naught is like the main attribute they're looking at. So now we're going into the solid solution strengthening model that they said that they were trying to create. So they found yield strength obtained by extrapolating the Hall Petch plot to a point of 0. Was used for alloy systems that didn't have a lot of like data available. The normalized intrinsic yield strength, which was their like sigma naught divided by Young's modulus, increases exponentially with increasing residual strain. To find that sigma naught, they use this equation. So the figure up at the top displays the different experimental data sets from literature that they found that correspond to their strain range of like the 10 to the negative 4 to 10 to the negative 2 that they used. They mentioned that they wanted to do a constant strain rate, but they're showing a slight like a range, which I think they were trying to go for constant and they couldn't keep it constant, so this ended up being like the range that they did their experiments at. I think it's fine. Like I don't think this is a significant change in range that would like really affect the like conclusions that came from this data. And then the middle plot there is calculated versus experimental data, and obviously since it's pretty clear like one linear match, they had a good match between calculations and experiment. So it's good for them. And then they realized that the presence of an additional solute species, specifically manganese, adds to the solid solution strengthening. So in the plot at the bottom, they included HEA1 and HEA2. HEA1 includes manganese, and HEA2 does not include manganese, which they don't mention earlier in the paper that they're going to take out one of the species. So I thought it was like kind of random for them to like mention it in the middle of the paper to be like, hey, we took one of these out, and then we did all this stuff and we found that, because I feel like I don't know, it was like a little odd. But yeah, so they found that like obviously I think increasing, because since this like solid solution strengthening, this like sigma naught is related to lattice friction stress, which is like, you know, I think related a lot to like solute atom structures and all that stuff. Obviously the more principal elements you have, the more like lattice mismatch you're gonna have. More lattice mismatch you have, which then increases like solid solution strengthening and like lattice stress and everything. So that makes sense. Yeah. Then they go into conclusions. Compression.
Question before. In the table 3, they say for the HEA1 and HEA2, the intrinsic yield strain is the average value between the one that they calculate plus references, right?
Where?
Just behind the table 3.
Yeah.
These values that they have for intrinsic yield strain, for the first and second one, this is not the value that they got. It's an average between the value that they got plus a reference.
Oh, okay.
So why they made that? If they need to show like their value, right?
Probably for like having statistically significant data.
So they just want to compare stuff.
Wait, both has two different.
Yeah, I was just asking. So they just want to compare different things.
Yeah, so they're trying to compare this intrinsic yield stress, which is kind of also the main like goal of this paper. And I'm assuming that they probably averaged their experimental data with literature because
But they didn't say which is the value. Okay, maybe we can look at
what their value was and what was in literature.
Yeah, because if it is really different, I mean.
Now, if they averaged it, I'm assuming they're similar because it would. Like,
should be right.
Rather than like taking like the mean or whatever, but it's probably because they wanted statistically significant data.
Yeah.
Is what I'm assuming. Is that what that star is?
Yeah.
Okay.
The A.
Yeah. Which is only for that HEA1 and HEA2.
Yeah.
Which kind of makes sense because I feel like those alloys probably have a lot less data on them. Specifically, the ones without like taking out and putting in like manganese or whatever. Because I'm pretty sure another paper, I feel like if I heard the name I would know. One of the other papers I think we did is a common class of HEAs that has manganese, and I think the one without manganese
is the common
is
one.
like less known,
common?
something like that. Yeah, but HEAs are also like a fairly new class of materials that don't have a lot of data on them. So it makes sense, like not make sense, but like I could see why they were averaging with literature.
Okay.
Because maybe literature had more theoretical work and they had experimental work on, or vice versa. Like they're like, oh, this is what we got experimentally, but we saw other people did this, or this is what we got theoretically, and other people did this experimentally, and they were able to combine the two. But yeah, I'm like curious what their value was versus what they had in literature.
They should show the value, right? At least it should be similar to be.
If they're averaging,
if it is not similar, that's something to
And
critique.
it's like, what is similar? Like, is it 5 off? Is it 10 off? Is it 50 off? Like, that's what I'm curious too.
Okay.
And HE1 has, well, in that one linear table with where they're comparing with literature values, it's like HE1 has like 3 data points, and HE2 does as well. So I'm not sure, like,
what?
Which one are you talking about?
Oh,
right
up
there.
here, yeah.
So I don't know if those are their values combined with literature values, and I don't know which was their value if that's the case.
Yeah. Well, it says
For which graph? B?
B,
figure.
B and A actually.
Because they compare experimental versus calculated, so you want it to be the same, but they're just showing that a lot of them aren't. I
Yeah.
think that's all it's showing.
And
But-
A is different experimental data sets across literature with theirs, like with what they just found as well. And they were looking at
Yeah, but they had three.
polycrystalline and single crystalline materials, like polycrystalline, CO, CR, Fe, Mn, and I,
Mm-hmm.
and polycrystalline are the same thing.
Yeah.
And so I think HEA1 is what they were looking at, and HEA2 I think is from literature because they.
But no, HEA2 has one doesn't have an MN. That's the thing.
Yeah,
Which
that's what I'm saying.
figure
Like, I don't
or
think
A?
they in their work were looking at HEA2. They're pulling that HEA2 from literature
Oh.
because in the work they only talk about making. They only grew the COCR, Fe, Mn, and I alloys through Bridgman, and they don't make the other one. They don't make HEA2. They only make
Interesting.
HEA1.
Okay.
Which is, I think, them trying to show that this, like, the presence of an additional solute alum manganese adds to the cell solution strength. Yeah, and then they did polycrystalline and single crystalline of the HEA1 is what they're just referring to. Yeah, then they like include across literature and things, all this stuff. Yeah, their conclusions are showing that compression testing showed typical FCC behavior, so they grew good crystals. The yield strength of both single crystalline and polycrystalline HEA1 alloys obey the Hall-Petch relation, which means, what we are expecting and what they found theoretically is happening experimentally as well. The higher value of intrinsic yield strength. Oh, it was shown that the higher value of intrinsic yield strength found there was a higher magnitude of the root mean square residual strain, and so they found that the intrinsic yield strength is more sensitive to atomic size misfit than the atomic modulus or than the elastic modulus is, which I think makes sense because intrinsic yield strength has more to do with the lattice mismatch versus the elastic modulus. The main focus here, as they say, or like one of the main takeaways I took from their conclusion was that the implication of this study is not that the lattice strain of HEAs is higher than that of conventional alloys, but that lattice distortion is proportional to the improvement of yield strength, which I thought was important because I feel like the first incorrect implication I definitely would have assumed from this, but they want to say that lattice distortion is proportional to improvement of yield strength. So they're able to achieve the strength of materials as high as their theoretical strength by reducing grain size is their main focus, is what they touch on. This was very weird paper.
I have a question on like the conclusions.
Yeah.
Like on a fundamental level, they say that the yield strength of the single crystals is less than that of the polycrystals. Yeah, just on the last slide.
Yeah, I'm just trying to see. Yeah, here.
Oh, they show a plot here which shows that. Okay.
Yeah.
So, like, on a fundamental level, why is that? Like, why do the polycrystalline materials have like a higher yield strength than the single crystals?
Because the lattice mismatch and the distortion of all the different principal elements together in the polycrystalline material, there's a high lattice distortion, which hinders the movement of dislocations, and so which increases yield strength. So those dislocations not being able to move means that you're not, there's like a lot of tension in those materials, but since it's like when you, just like built a piece of furniture that I feel like just did this. When you put two pieces of metal together and you have to put a little bit of weight and then you attach them, the tension that is like now placed on that connection adds to the strength.
Yeah.
So that's why they're showing like this what's it called, this elastic point, because they're trying to, like, you want strength in the elastic region, because once you get to the plastic region, then you start to like change shape, and that's when you get dislocations. And so they are hoping that this this high lattice distortion will still allow the material to be in like that elastic region where it has like tension and high level of stress, but without breaking into a plastic region where it starts to have all these like dislocations and slips,
Right.
and then they're able to have a higher yield strength.
Yeah. Yeah, that makes sense. Yeah, because like single crystal materials, like even just the comparison between the two, they are applied in different applications based on like this. And sometimes like single crystals can be strong, right? But then when there's the presence of like some dislocation, then there's no obstacle to
Yeah.
its movement. So
Yeah.
then it just continues.
I think that's the main
Yeah.
point here in this article,
Yeah.
because it's not
Yeah.
intuitive, it's counterintuitive. So
Yeah.
if you go to
Yeah.
the figure
Yeah,
6,
it is very counterintuitive. I
yeah,
don't-
figure 6, you see, D is like the grain size, right?
Yeah.
Like the negative 1.5 grain size. So if you see, if you decrease the grain size, what
Mhm.
you increase the yielding strength, right?
Mhm.
Because it's 1 over D to
Yeah.
the 1.5 power.
Yeah.
That's the most important plot for me, because it's
Yeah.
counterintuitive. So in this
Yeah.
case, the polycrystalline one
And this
will have.
Yeah.
this
That makes
relationship,
sense.
Yeah.
That
this
makes
like
sense.
Hall Petch plot is like a known relationship for materials. So I feel like
Yeah.
really understanding Hall Petch plots and like what they mean, which is decreasing grain size,
Grain size.
increases yield strength.
Yeah.
Yeah.
Well, do you know about failure
It's-
mechanics and all that?
Huh?
Do you know about failure mechanics and all that? Like what usually happens?
Yeah.
Yeah, so you know why that is.
Yeah.
Okay.
I mean, you can explain if you want to.
Yeah, it's
but
just like the decreasing grain size means there's more grain boundaries.
Yeah.
And so
Yeah.
like it's harder to penetrate grain boundaries at a crack than it is to penetrate through an actual grain.
Mhm.
Yeah.
So it favors more
Yeah.
intragranular corrosion than intra, right? Not half corrosion.
Yeah.
Forget.
Say it again.
Yeah. It's like in ceramics that you don't want like a completely a really dense material, because the pores, the little pores that you
Yeah,
get in
yeah.
ceramics, especially with thermal work, is like you hit a pore and then that like crack or that growth
propagation.
stops. And so you don't get it like cracking throughout your entire material.
Yeah.
And so having defects, or like having more grain boundaries, when like a crack or like some defect starts to form, it hits a grain boundary and then stops, and it doesn't like continue on through the rest of the material.
Yeah.
Which is the polycrystalline part of it, where like you
Yeah.
have all these really small grain sizes and all these little lattice
Yeah.
mismatches that like when you have points of tension that start to like form, they hit a grain boundary and then they stop, and then it allows for like an increase in strength.
Yeah. Yeah. That's the whole point. I guess.
Yeah. So yeah, this was a short paper. I don't know. Possible questions: stress strain curves. Oh, I should have mentioned the Hall Petch. Yeah, that's what me understanding graphs is referring to, the Hall Petch plot. And then they mentioned this like manganese thing, so I thought maybe the effect of doping or lattice mismatch or mechanical properties would be good. But
I have a question.
mhm. Oh, so I didn't include it because
Yeah, I saw it.
they mentioned pole figures, and it was just their way of like showing that the slip directions were happening, or the slip systems were happening in certain directions or whatever, that they were growing their materials in the right direction.
Wait, isn't the pole figures literally just confirming the direction of those?
Yes.
Yeah.
Yeah.
I know nothing about slips
So that's
yet.
why I didn't include them. Also because pole figures, I think, are really difficult to understand. I literally, when we took it in scattering, didn't understand a single thing about it. I even
That's
looked
fair.
back at my notes and I was like, I don't get
I
it.
mean, they might ask, like, what's what
Yeah.
on the diagram. Or
So,
even, like, look at the EBSD and orange, draw the pole figure for the orange segment. Of
which would
EBSD.
be insane.
Yeah.
But like,
It would be mean.
it would be so mean, but yes, I guess, like, I don't know. I just feel like that would be such a, I guess it would make sense because they do include pole figures in this paper.
Yeah.
So they'd be like, can you draw the pole figure for this? Which, yeah, I guess I didn't consider to be a question because I was like, that doesn't even relate to like the actual purpose of this paper. So I'm like,
A lot
that
of
would
the
be
practice
crazy, but-
questions don't.
Yeah. So
Like,
that's the
they're
thing is
completely
like,
unrelated.
you don't know why they pick a paper. Like they could have picked a paper because they only wanted to talk about
in
like
there.
the first half of the paper, or like the whole solution, or like a single graph in the paper.
Yeah, you know, like,
I would say it's really a good question.
I feel like
I mean, I
Well-
looked at the sample thing this morning, and
Yeah.
it was more geared towards background information.
you know what they might ask. They might ask why is the pole figure for the polycrystalline, or explain why the pole figure is different for polycrystalline versus semicrystalline.
Yeah, and that
Yeah,
Which is
I feel like
totally
that's-
fair.
that feels more
it
related.
has something to do with the paper. Yeah.
So I was reading over thermo, and maybe entropy of mixing could be on this as
Yeah.
part of.
okay, yeah, high entropy alloys.
So then there's like a lot of degeneracy and like statistical thermo and stuff.
But like that's not even. They talk about literally nothing about that.
Yeah, I know. I don't
That's true, but that's
But,
the
yeah.
background
That's something.
behind all of this.
A lot of the questions on the sample exam were thermal based.
Not to mention that he does, what's his name?
Locally?
Yeah, Gokuli
Yeah.
talks about lattice, not necessarily, he talks about lattice mismatch and the, like, the Hume-Rothery rules and stuff like that. And,
Yeah.
yeah.
I think like for high entropy alloys, definitely like the Hume-Rothery rules would apply to any paper on this because like they mix like different things together and like specifically for the manganese like thing, why did they choose manganese?
So it'd be cool to know, like, all the.
I mean, why did they choose manganese?
Yeah.
Who knows?
Yeah, who knows? Like
I don't
then
think
you
that's
have
a
to
fair
go
question to ask.
to go and think about many other things.
It'd be interesting, though,
I mean-
to know, like, the atomic radii and lattice
Yeah,
parameters
yeah.
and all these things.
The atomic
They'd have to
radii,
provide it.
electronegativity, all those things you have to think
Like
about.
again, they'd have to provide all that. You know what I mean? Like
Wait,
Yeah.
was this wasn't a past paper, was it?
No,
No, I don't think so.
you could find papers similar to
But I feel like they've had papers similar to this in past years.
yeah. And I think at the end of the day, those are some of what you should be looking at to kind of gauge what they probably ask you, aside the knowledge on the paper.
What did they ask him, though? So I kind of skimmed through the older exams.
Like for these kind of questions, I've seen like it's calculation like the slip systems, right? And when I look at some solutions, like I've seen like some people do like some kind of thing in the past on these questions, and the solutions are pretty simple, like just like two-step solutions, but we don't have any idea about like how to go about it.
There is like 3 hours worth of videos from the guy teaching the slip systems, and I don't know.
3 hours? What?
it's just not.
I'm not the.
Yeah, like because like you don't even know if it's gonna be if it's gonna be worth it. Yeah, so well, yeah, if you wanna do this paper, I think you should also look at the calculations just in case. Just in case.
This is the thing. That's why this is in my maybe pile because I'm like, okay, I understand this paper, but like, do I understand slip systems? No. Do I understand the pole figures? No, not really. There's a lot of little stuff where I'm like, I don't really know if I want to focus my time in learning all that.
Okay.
When like I understand the paper, but like the background stuff, like deeper into it, I'm like,
Yeah.
I don't know if I wanna
There's
do it.
some calculations, and I've seen about 2-3 questions in the past about dislocation loops.
Oh, really?
Yes, and yeah, they just ask like, what is this dislocation loop, and if this is blah blah blah, then you use like some equation to solve it. So like, yeah, you can read on dislocation loops. That's one of the reasons why I didn't want to do this paper later on, because I was like, I don't think I have enough time to
This is
go
going
over.
in the no pile.
But there's this one. What do we call it?
Yeah.
If you go in the exam and they don't ask calculations, definitely you can do it.
Yeah.
I think there's a document in the drive there somewhere where people will say like things to know for course or something, and so there's a folder or something on dislocations, and they kind of explain. And I think that Professor Kacha, he had a class. They said it in the course panel. He has like a class where he teaches people about the dislocation. I think last year they did like a day or two to review dislocation, and so someone has notes on them. I couldn't really see the handwriting, but yeah. So they teach like just like fundamental things you should know about dislocation that would be relevant for course. It's like 30 slides or something, but it could also be hard. So you can check that. All right.
How many old exams are there floating around?
I've seen
I saw the
between
one that they-
2012 and 2016.
Because they
2017.
posted one for us through Teams, like the department, and then I saw that in the past there was others, but I don't know how many there
Oh
were.
yeah, interesting. I haven't gone back to check the teams one. I